everyone, my name is Maria and I am today the host of the talk of Professor Jo Verbeeck, which is a part of our 4D STEM workshop. So Jo is holding his position at EMAT at the University of Antwerp, and as maybe a lot of you know, he has a huge experience in both the application side of advanced microscopy as well as the developing the new techniques both in hardware and software. So, Jo, I think you can take over. Thanks.
Thank you very much, Maria. So what I will try to do today is, and I understand that you had an introduction in 4D STEM and so on, so I will try to focus now on the detector side of things. So I'm trying to take a practical approach and explain you what choices you have in order to actually make 4D STEM on your microscope work and what kind of cameras you need for that. In this respect, I'm not representing any company. I will stay rather superficial. I will mention some company names here and there, but I'm trying to focus on the principles and on the different kind of technologies that are out there. Very briefly, with 4D STEM, and you have had previous webinars on this. So you're basically recording a scattering pattern when a focused or an unfocused electron probe hits a sample and it creates a diffraction pattern. And you then have a camera that records this diffraction pattern. And then you're going to 2D raster scan this probe and record many diffraction patterns. Now, the beauty of this technique is that it in a way records all the scattering information, at least on the elastic side, that is available from the sample. So it's a hugely it conveys a lot of information about the specimen, and you record it all. But that means it's also very data intensive. You're going to produce an awful amount of data, and we need to think about how to do that. It's very challenging for the speed of the camera, because typically you want to move the probe with, let's say, every microsecond you want to go to a next position. So the camera has to be ready to read out its frame in such short times. And then you produce a lot of data, so that means it's also very challenging on then trying to make sense of all this data and do some data mining and trying to find the information about the sample that you're after. You could question, like, why is this all happening now? This has a lot to do with cameras, but also with storage of high volumes of files, processing speed, and technology is just ready for it now, and it wasn't, let's say, 10 years ago, and definitely not 20 years ago. Okay, so cameras and technology of cameras is important, therefore, for this STEM. So let's take a deeper look. So you have two major types of principles of detecting electrons in cameras, in electron microscopes. There are other ways of detecting electrons, but they are more exotic. So the easiest way and the most common way up till a few years ago was using a so-called scintillator. So in a scintillator, you have a layer of material where if an electron hits, it causes inelastic scattering. It excites atoms inside that layer, and these atoms will de-excite and emit photons, and these photons will then travel to an optical camera. So that means the nice side of this is you basically can use a commercial optical camera. You just stick a scintillator in front, and in a way you can make an electron camera like that. Detector quantum efficiency, that means so how many of the electrons that actually land on the camera are basically recorded. That is sometimes not so great. It depends really on the technology and how perfected this is. The nice thing is the scintillator basically can be replaced. Some scintillators, after, let's say, illuminating them with a lot of electrons, they wear out, they fade basically. And so in principle, you can replace the scintillator and you have a new camera again. There is a problem sometimes with afterglow. That means so if you really put a very intense electron beam on these scintillators, they tend to keep emitting photons long after the electron is gone. And this is, of course, very bad because in 4D STEM, you want to move your probe very fast, and you don't want to get information from 1 millisecond ago because that's several hundreds of probe positions ago. So this afterglow can be really problematic for 4D STEM, and especially so the more you make things that look like diffraction patterns on these cameras, the more problematic it will be in these very intense points. There are issues with saturation, linearity, dynamic range, so it is not guaranteed that the photon output is completely linear with electron input. There is a maximum electron input where there is no more light coming out and so on. So these are things you have to take into account, and these make that not always interpreting this the output of such cameras is straightforward. The point spread function may also not be ideal, and what we mean with point spread function is basically when an electron hits on a very specific point on the scintillator, photons are produced in all kinds of directions, and on the camera it may illuminate more than one pixel for this single position electron input. And this means it will cause a blurring in your final image, and it often means that, for instance, if you have a 1K by 1K camera, these million pixels are not all independent, but maybe you only have one third or even less of the pixels which are basically meaningful because of this blurring effect. Scintillators can be slow. There are very fast scintillators as well. And slow is not good for 4D STEM because you will be scanning the probe fast and you want to detect really fast changes. Then recently it's become more modern to use so-called direct detection, where basically an electron hits a semiconductor and creates an electron hole pair directly in the semiconductor of the detector. So there is no intermediate in first going from electron to photon. You directly go from electron to electron hole pair, which then creates an electric charge or a current, and which can electronically be converted into a signal that your computer can eventually read. If you think about it, if you have electrons above 10 kilovolt, and in TM we have electrons easily above 100 kilovolt, they will create several thousands of electron hole pairs in silicon. And that shows how this is a very favorable way of working, because sure, there is thermal noise and there will be electron hole pairs generated in the silicon just because of the temperature. But because electrons are so energetic, or at least the ones we use in TM are so energetic, you create so many electron hole pairs that it is not so hard to, with certainty, detect them above the noise level. So this makes that you can really make a single electron detector. So that means that your detector will go off when a single electron lands, and it will not go off if no electron lands. And so imagine now you have a very low light condition or a diffraction pattern with only light in one area of the sample. That means that all the area which was not illuminated, which didn't receive electrons, will read 0 and not some noise level, some dark noise like you would have typically in scintillator kind of cameras. But it will really be truly 0, and that from a physical perspective is very nice because we can really get all the information. We have something that comes really close to an ideal quantum detector, basically. The downside of this is you have very energetic electrons. You hit your silicon or whatever other semiconductor that's used, is that these electrons can also, they have more than enough energy to damage the camera. Which begs the question then, how long is this camera going to survive this electron bombardment? So you're basically kind of mistreating the camera. And a solution for this, well, there are basically two solutions for this. Either you separate the detector layer from the electronics. That's what's done in so-called hybrid pixel array detectors. Or you make the semiconductor layer, the chip that consists of your camera, really thin, so that most of the electrons just go in, they leave a bit of energy, but then they go through the camera. I think for 4D STEM, the separate layer is fundamentally a better idea, because your detector layer is separated from the electronics, and we will come back to this in some later slides. Then, besides the question, how do we detect the electrons, there is also different technology in basically how to figure out where electrons landed on the detector. And traditionally, a charge-coupled device, or CCD, was the most common way. So basically, there is a picture about this works here. So you have an array of pixels, and then you have something that looks a bit like a shift register. So let's say we create a charge here when an electron hits that pixel. So you create a charge, and now we want to read out this charge. So then there is something that acts as a shift register that can shift the charge to the next pixel, then the next pixel, and the next pixel. And then you can read them out in the other direction, and eventually you can amplify and turn them into a digital signal one by one. Okay, this works, and this was the de facto way of working for a long time. CCDs are claimed to be low noise, but I'm not sure in the current landscape this is still, let's say, really a defining difference. They are fairly simple chip design because the pixels themselves only need to contain this kind of shift register. There is no real electronics going on in the pixels. The only electronics is here in the part where there needs to be a fast amplifier and analog to digital converter. They are quite beam hard because the electrons never hit really the electronics, but they only hit the, let's say, the electrodes that make up the shift register. But annoying thing with these cameras is that there is influence of charge on neighboring pixels. And this is very problematic, especially for diffraction patterns, so especially for images with a high contrast, is that you will get streaking effects, and depending on the direction in which you read out, you will see that the behavior is a little bit different. So for conventional images, this works fine, but for diffraction patterns, and especially for high intensity diffraction patterns or high contrast things, this can really be very problematic. And the faster you read out this thing, this could lead to generating electromagnetic noise, which will create some background noise which isn't wanted. So that would mean that the faster you read them out, the more likely it is that some of this readout noise will also enter your signal, and this is something you don't want. More modern, well, they are not so new, is the CMOS detector. And the CMOS detector is basically depicted here. So in a CMOS detector, every pixel has a little bit of its own electronics. And sometimes it's only a little bit, and sometimes there is a lot of electronics there. And this makes use of the huge, let's say, progress that has been made in digital electronics. We can now squeeze a whole lot of electronics in the size of a few micron by a few micron pixel. And that means that, for instance, this first amplification stage at the very least, but we will see later more complicated solutions, is done on a pixel by pixel basis. And you're all very familiar to these detectors because you all have them in your mobile phones. So they are a very common way of making a camera now, and the CCDs are in a way getting more of a niche market for the scientific market. Each pixel has its own electronics, I said that. That means it can be very fast. There is no kind of shift register readout or so. Every pixel can take care of its own business and make decisions already. Because of CMOS integration and the enormous level of miniaturization that is common in the CMOS technology, it can have very small pixels. So in your mobile phones, the pixels are about a micron by a micron, and you can have several thousands by several thousand pixels. And that gives you a very nice small camera, which can still have amazing, let's say, a number of pixels. Image processing can happen on chip because you have digital technology there anyway, so you might as well not only detect the hits on a pixel, but you might also have a counter there or do something with the data already. So you can have immediate, let's say, decision making on whatever happens with your camera on chip. They can be cheap, that's why they are in your mobile phone. That's especially true when they're small. For scientific applications, you probably want bigger pixels and bigger, let's say, die size of the camera, which probably will mean that they are not cheap anymore. And they are very low power, which is also, again, for your mobile phone, a very important feature. So then there is the question of the number of pixels. So okay, you want to do 4D STEM. You're used maybe to more conventional imaging where megapixel cameras and much more are very common. And you could wonder, like, okay, how many pixels do I really need for 4D STEM? One way to look at it is that the information per electron is something like 2n bit, with n being the number of pixels in one direction. So if you have a 256 by 256, then basically when an electron hits on a specific pixel, you can convey that information by giving an x and a y coordinate in 2 times 8 bit, for instance. But the area and the price of the chip, they go as n squared. So in a way, the difference between a 256 and 1K camera is only something like 25% more information on exactly where the electron hit. But it is a 16 times more bigger area, 16 times more data to send to a computer. For tachography, this will determine the sampling in reciprocal space, and it really depends on exactly how you set up your 4D stem. But it turns out, in most cases, I would say from about 128 is plenty, unless you are targeting really large defocused probe tachography. So a few hundred by a few hundred pixels is already very luxurious. Going to, let's say, 10,000 by 10,000 pixels will rarely make sense for the stem, and will probably lead to a camera which is not able to let's say, transfer out this data fast enough. So there is a trade-off, of course, between camera speed and the number of pixels. And what we see now is that actually the cameras with fairly low amount of pixels are rather popular and fast. There is a trade-off you have to think about it. So maybe there is more you want to do with this camera than only tachography. And if you want to do diffraction, or maybe at some point also TM imaging, you will want to have a little bit more pixels. So you have to think about, is it like single use for the stem only? If you want to do serious diffraction work, yeah, you want to know with fairly high precision where your diffraction spots are. And then you probably want more pixels than 100 by 100, but that's a trade-off you have to make. Okay, then these cameras have things like PSF, MTF, DQE, NTF, and a lot more performance parameters, which are not always very well communicated with let's say in the product leaflets. So let's look at the more important things here. So first thing is the PSF is the point spread function. So when a fast electron hits either the detection layer in a hybrid pixel camera or the detection layer, a scintillator, basically, what happens is that the electron undergoes many inelastic scatterings, and it's a rather chaotic path. It follows through this layer and it generates a signal. You can imagine that that means that even though the fast electron hit exactly here, you still get hits or response from the camera over this whole cloud of interaction. So you see it will depend on the silicon detector layer thickness or the scintillator thickness if you want. And this will make that sometimes when a fast electron hits in one point, it will also trigger the neighboring pixels. And this is this creates a kind of a point spread function. So this makes that what was once a sharp image, let's say all electrons hit exactly this one point, that the image of that will look like a broader distribution. And that distribution is the point spread function. So it's basically the response of a point-like input and seeing what is the output on the camera. So here I have some examples from these papers below. This is, for instance, on an MPET camera. So you illuminate an edge, basically. So there is intensity here in the top part, and there is a blocking edge on the down part. And so if this would be an ideal camera, then you would have, you see electrons, so you have intensity here, and it would go immediately to black at this sharp cutoff. And that you see here, and basically you see that the cutoff is pretty fast, but it depends on the energy of the electrons. So at 80 kV, the edge is pretty sharp, and you can try to determine. So it's basically what you get is a convolution of a perfectly sharp edge with this point spread function. So you can turn it into actually by, if I'm not mistaken, differentiating here, you will get this point spread function, and you see how ideally you get a response that would be only that single pixel here from -0.5 to 0.5, which is more or less okay for 80 and 120 kV. and the lower the better, basically. But for 300 kV, you start to see that it has quite big tails, which means some of the intensity is leaking out to the neighboring pixels. And that's understandable because you bring in more intensity, more energy, basically, and the electron will scatter further away. So this is something to keep in mind, that depending on the energy you will work with, it might have different properties. And this property is important because it will blur all your images with this point spread function. So that will make that, especially at 300 kV here, you have to be a bit careful about that. There are ways to work with this because when a single electron hits, you will get, in such cameras, you will get multiple. So this is a hybrid pixel camera also. You will get multiple hits. And in a way, if they all happen at the same time, you can use this to do so-called declustering, and because you know that all these hits belong together, and you can work out back to the let's say to the center of mass of this event, and then you have tricks to really sharpen this up and to correct what looks like a downside here at 300 kV to turn it into your advantage and actually get very good response also. But you need this correction step then. If you Fourier transform this point spread function, you get the so-called modulation transfer function, which you see here. And you see the dotted line is what an ideal detector with square pixel would look like. So you have a response which tapers off a little bit to higher spatial frequencies. And you see how close this camera gets between 80 and 120 kV, how close it gets to ideal. And this is why 4D STEM is really happening now. We have really detectors now that are almost like a quantum operator of a measurement, basically. They come very close to the very best you can hope to get. And again, you see the effect at 300 kV that there's a lot more suppression of the high frequencies. So to your image, it will look a bit like a blurring effect or a low pass filter that is happening there. But as I said, this is not the end of the story. You can actually, with declustering, you might be able to push this line all the way up again, depending. There is then DQE as detector quantum efficiency. So this is basically how many, if I send in 100 electrons, am I really going to get a signal out of my camera that will convey 100 electrons, and that will have the noise and the Poisson noise that will belong to detecting 100 electrons. If I have more noise, if there would be some background noise, for instance, then the DQE would go down because I get more noise than you would normally get from detecting 100 electrons. Well, there's a lot more to be said. It's not always easy to get such plots. Typically, they appear rather in papers by scientists evaluating these cameras rather than that you easily get them from vendors, let alone that they are presented in a way that you can easily compare them across vendors. So this might be a bit of a challenge. There are many other important parameters, things like the frame rate, how many frames per second can you record, what is the maximum current, electron beam current the detector can handle, are they beam hard, are you allowed to put a certain current on the beam and leave it there overnight without damaging it, or do you have to be careful about this? That time is important, so there might be a time when you're reading out the frames that you are not recording electrons, and you could say, oh, okay, that's okay, I have plenty of electrons anyway, but you have to realize that while the camera is not reading out, you might still be damaging your sample, so it's a bit a pity of all those electrons that created damage that you're not using this information, so you have to be, you have to ask yourself, what is this dead time? Is there dark noise? So that means if there are no electrons hitting the camera and I read out frames, are they really zero or do I get noise? And this noise is something we don't want, especially not for low dose imaging. We really want that it is zero then. But depending on the camera, there might still be a little bit of dark noise. Dynamic range is important. So what is the range between the lowest signal you can detect and the highest signal you can detect? This is especially important if you want to put diffraction patterns on your camera where dynamic range can be enormous. So that's something to look at. And something which is typically deeply hidden in the documentation of the camera or when in the process of buying a camera is how many bad pixels are you to expect. So maybe you would think like if I order a camera with 256 by 256 or 20 megapixel or whatever, that all those pixels will be, of course, good. But it turns out this is not the case. This has something to do with the yield of the production process, where it's actually very hard to predict that everything will be perfectly okay. And typically, when you read the details of a camera description, the vendor will allow a certain percent of pixels that are behaving different, that are either a little bit less sensitive, or they might not work at all. And that's something to read carefully. In many cases, you can get 100% good camera, but there is a price difference between, let's say, A and B level cameras, whatever. So that's something to also be aware. Otherwise, you might be surprised later and you think, hey, I have bad pixels, I didn't order this, and then maybe they tell you, yeah, yes, but it's less than so much percent, so it is still within what we promised. I asked my student, Arno Anes, to make an overview of the current cameras on the market, basically. And I don't want to go into all the details that you see here, and also you should take this list as just a representation. What I want to convey with this list is basically there are so many parameters and so many choices. So choosing the right camera for 4D STEM is not an easy task. And there are many parameters, and depending on what you really want to do, one might be better for you than the other. But just to say that there is a lot of options out there, and figuring out what you need may not be as easy. So what do we want to focus on for 4D STEM specifically? We really want ultra-fast frame rate. So we want the frame rate to be equal to the dwell time. And in STEM, typical dwell times that starts to be useful are, I would say, 10 microsecond at the slowest, 1 microsecond preferably, sometimes even faster. You really want your frame to build up quite fast. So that means you want a camera that can follow these frame rates. So the higher, the better, I would say. Ideally, we want no dead time at all, because all the electrons that hit that hit the camera, I want to record them. I don't want to throw them away. I probably want a high dynamic range, because I will have a strong diffraction peak or diffraction disk in the center, and then nothing outside. So dynamic range is probably important. What is very important is it needs to be beam hard, because you're putting diffraction patterns on there. And maybe you could say, yeah, but I'm using always focused beam CBET, so it's not a diffraction point, but a disk. Yes, but you don't know what some other user will do by accidentally illuminating the camera in diffraction mode with a parallel beam. And then the camera needs to be able to withstand that. You don't want to be afraid with, especially not in a lab where you have multiple students that are all learning about these cameras. It's good to have some peace of mind that you have a beam hard camera. What you really want also is that the noise of the camera is strictly Poisson noise, which means that you have a camera with a high DQE, and you really only want to have you want to be counting electrons, and you don't want to be seeing thermal noise or readout noise or things like that. So as I said, something like 100 by 100 pixels should be enough for the STEM, but it all depends what you want to do. That also means that pixel size can be fairly large, because you still will have a camera of, let's say, a few centimeters by a few centimeters. So that means if you only need 100 by 100 pixels, you can have fairly large pixel sizes. And that helps with the modulation transfer function. That will make that this sideways motion of the electrons that are hitting the detector is not too bad. And that means you can, and you will benefit from great modulation transfer function. And that's important. Then you also want good trigger capabilities, because you will want your scan engine, the probe, moving step by step. It needs to be able to trigger with the camera, and that needs to, you need to be able to set that up. And then you need to do something with this camera data. So, so when you look at the software that comes with the camera, that's important. So either you look at something that takes care of the full 4D STEM workflow, but as far as I'm aware, this doesn't exist at the moment. or you look for software that is open enough that you can create all this yourself. And so very likely you will have to do that. So make sure that then the software that is shipped with the camera allows you to get the data of the camera in a way that you need it in the software that you will either be developing yourself or you will be sharing among researchers. So something more about this hybrid pixel array detector. So here is a schematic of this. So you have the detection layer, and basically the electronics and the amplifier, maybe some counters and so, is sitting on a different chip that is ball bonded together to the detection layer. And the beauty of this is that the detection layer, which will get all the energy of the electrons, doesn't contain any of your very small scale transistors and so on that would degrade otherwise, and that would cause make the camera go bad after a little while. So most often this layer is silicon, but you sometimes have choice. Something typical thickness is 100 to 500 micron silicon. The choice of this thickness will dictate how well the camera works at certain energies. So there's trade-offs to be made here. Internally, here you see a beautiful schematic on how things internally work. So basically, when you get a hit in this pixel, it will create an electronic pulse here. This pulse needs to be amplified, and here we get the beautiful effect of the single electron detector. This pulse is so high compared to the thermal noise that with a comparator you can set a threshold and you can really detect, yes, it happened now. So you basically turn what was originally an analog signal, you turn it into a digital signal that tells you, yes, I received 1 electron. And then now you're in the digital domain, and then you can make use of all the beautiful possibilities in CMOS. You can put counters, you can put complicated digital electronics behind it to do something with these events. So basically every pixel could have its own counter, and you can detect, okay, on this pixel I received 5,000 hits basically, and this pixel remained silent. And then the challenge is still to get this data off to your computer, and the bandwidths of this are becoming really enormous at the moment. But okay, you see the beautiful aspect, and you see how difficult this is also from just staying in the analog domain and just analog to digital, converting this analog signal into a noisy image as before with CCD cameras, for instance. But now you really detect event per event, and from then you leave the analog domain and you really are working with electron events, basically. Something about synchronization. This is ultra important for the STEM. You want to move your scan engine, and at the same time, your camera needs to know that I'm now at a new position and I want to record the diffraction pattern. You could think like, okay, but I can set my scan engine to do, let's say, 1 microsecond dwell time. And if I choose the exposure time of the camera also 1 microsecond, then things are fine. They're both equally long and things will work out well. Now you have to realize that the clocks in both the scan engine and the camera and in anything else that works digital are made by crystal oscillators, and they typically have accuracies up to something like 100 ppm. And they have drift with time and temperature and so on. So that means the clocks of your scan engine and your camera will not be running in better than, let's say, 100 ppm synchronization. And if you're then going to scan 1,000 by 1,000 points, then you have recorded 1,000,000 points. And if you want to have everything in synchronization, that would require a clock, let's say, precision between the two clocks to be better than 1 ppm, which is not impossible, but is definitely not the case in the current electronics. So this doesn't work. So you cannot start the scan engine and the camera at the same time and hope that that just because you asked both to be 1 microsecond per dwell time, that the synchronization will work out fine. And this is shown here in the bottom. So this is actually experimental data where we show that if you do the synchronization right and you do a 1K by 1K image, that you get an interesting reconstructed image. Now, if you get your timing off by only 1 nanosecond per dwell time, you already see that you create something that almost looks like a dislocation here or something wrong in the image, and that's at 1 nanosecond too much and 1 nanosecond too low, and you see your data completely messes up. And you see how dangerous it is, because you might be starting to think about, hey, what's going on in my sample and so on. So you really have to get the synchronization right. So what you can do is you can use line sync. So you can make a synchronization pulse every scan line. That would work because, let's say, if your scan line is 1000 pixels off, then you would need a clock precision of 1 in 1000, which is okay. That's in this 100 ppm level. That would work. But pixel synchronization is by far the best. And then really every pixel is resynchronized basically, and then you're certain everything will be good. An alternative way to show this, but that's not how things are done right now, but it's more some idea that could come from a synchrotron community, for instance, is to have one common shared lab clock, and then all devices only need to know the exact time, and then you can later in software work your way back what happened at what time for each individual instrument, but you don't need to have the synchronization lines running between images. But this means you have to, in order for the synchronization to work, you need to be able to set up cables between your scan engine and your camera. You need to be able to figure out, like, okay, what triggers are sent out, what triggers does my camera need, and so on. So this is something that requires attention. And it involves information from the camera vendor, from the scan engine vendor, if that's different from the camera vendor, and from the camera. So that requires attention to make sure that things will work together. Then, if you think about for this STEM, we are recording these diffraction patterns. And, well, there is this beautiful paper here by Spurgeon et al. That shows how, over time, we have started to record more and more data in a shorter and shorter time. So we had film camera before, where you take a few films, and in the evening you have to develop those films. And then you have CCD, which had like millisecond, typically, frame times. And then you get higher and higher. And now with direct detection and specifically for the cameras, the number of frames per second is increasing. But that also means that the data these things output, here it's in gigabytes per hour, really becomes enormous. So a camera like here was portrayed here in 2020 already can produce 200 terabytes per hour. So you have to think about, okay, it's all nice that I'm going to produce all this data, but do I even know where am I going to store so much data, and how am I going to deal with this data, and so on. So there is, so some people would say, like, yeah, for this STEM, at some point there's going to be a data crisis. It cannot keep expanding like this. That's what brings me to an important difference between some of the cameras that are interesting for 4D STEM, and that is the question whether you read them out in an event or in a frame-based mode. So in event, let's first look at frame-based detectors. So frame-based is what you're used to. You basically says, yes, take an exposure of 1 microsecond or 100 microsecond, whatever, and you save the frame as a matrix, and you send it to your computer. So let's take as an example a 1-bit Merlin camera, which seems to have, and don't, let's say, pin me to this number, but let's say it has a maximum speed of 80 microsecond, and you save the frames. So let's say now we want to do 10 times a 1K by 1K scan. That would take 13 minutes to record because of the maximum frame speed, and it would produce 1.2 terabyte of data. If, on the other hand, we use the so-called event-based detector, and an event-based detector will basically only save when an event happens. So it basically, rather than sending out a frame, it will always, when an electron happens, it will send to the computer, hey, I got an event in position X, Y, and it happened at time T. So you basically just get a stream of events telling where the electrons landed and at what time it happened. Maximum speed, I say here 30 nanoseconds. Some can do a few nanoseconds, I think, but it is fairly fast, and you save the individual events. If you now do the same scan, 10 by 1K scan, we can use 1 microsecond dwell times, because basically the event speed is now completely decoupled from the frame rate, basically. So all you need to do is just wait for electrons to land. And so we can choose a dwell time now for 1 microsecond in the scan engine. And this will produce 3 gigabytes of data if we use a beam current of 2.6 picoamp. This 2.6 picoamp is on the low side maybe of what you're sometimes doing, but this is a limitation of these kind of cameras. They have a certain maximum number of electrons per second that can hit a sample. The maximum for the camera we were using here, Timepics 3, was 4 picoamp. In future, this may, there are new generations coming up where this can be increased a bit, but always event-based detectors will have some limit on the number of electrons per second they can receive. Moreover, frame-based detectors also have that, but these limits are higher. Okay, that's the thing. But you see the difference between event-based and frame-based is that you can do fundamentally faster scans. So basically, you're no longer limited to minimum dwell times or whatever that the frame-based cameras would enforce on you. And you have something like natural data compression. You see here, if you were recording frames, these frames would be mostly filled with zeros, basically. But it would fill up, if you don't do any compression or so, it would fill up 1.2 terabyte compared to 3 gigabyte of data. So that means you get this natural compression. And the beautiful thing in an event-based camera is that your data file that you generate will depend on how many electrons you had in the image. So it's basically only giving you the information that was there in the image and nothing more. So if you turn the beam current down, your file size will get lower as well. As we will see, these higher scan speeds are important because they can, of course, reduce specimen drift. And this is important because yeah, here you will be recording at something like 100 microsecond dwell time, which leads to really slow image recording, and anything that drifts at the time will skew your image and so on. But we'll see that it also lowers damage. And lower data size eases a lot of things like processing, storage, and transfer of this data. So there are many benefits in doing this here. But keep in mind that there is one, let's say, limitation, and that is how much electrons per second we can deal with. Here is another way to look at it. This is how many scan steps we're going to take in one direction. So let's look at a 1K image. Then if you're working in 16-bit frame mode, that will be just under a terabyte of data. If, on the other hand, you do event-based and you use 10 picoampere current, you will have a significantly lower file size. And of course, then it depends on the current you're using. And then these 10 picoamp and 100 picoamp, don't forget that the current event-based detectors can't handle such current, so they're even lower. But you get this natural data reduction. But it's not only data reduction, it's also when you look at, okay, now I'm going to have to deal with this data. I'm going to process this data. Then you can show that depending on what you do with the data, for instance, if you want to make a virtual STEM image, that's basically just grouping a number of pixels on your diffraction pattern together into an intensity to portray as a conventional STEM image, basically. Or you want to do center of mass, then in frame-based, it doesn't really matter what the dwell time you used won't change the number of operations you have to do on this image. But in event-based, the lower the dwell time, the less electrons you have per second, basically. The lower dwell time you have, the less events you have in these frames, and therefore you need to do less operations to reach to your result, for instance, for virtual STEM. So you need to sum up less events, and you see how the faster you go, the more event-based is let's say, advantageous over frame-based recording. Of course, the caveat here is that there are frame-based cameras that are looking into compressing the data. It's, of course, silly to send out a matrix full of zeros without maybe just sending, hey, I have a zero matrix. So there is definitely a huge room for compression algorithms here, which will close the gap also between frame and event-based eventually. Okay. Good. So here is an example on how it would look with an event-based camera. So we used a Timepics, a prototype Timepics 3 camera here, which can do event-based, and we compare an image, a 4D STEM data set recorded at 20 microsecond dwell time here. And we can reconstruct basically an image. We can look at the diffraction pattern, the average diffraction pattern for the whole thing. And we can do 20 microsecond scan, fairly slow. But we can do the same thing. Instead of one time 20 microseconds, we can also do 200 times 100 nanoseconds. So the total electron dose is the same, but rather than scanning once, we scanned 200 frames very fast. And you see an individual frame would be very noisy, basically, but you see we can still get the same data. What you notice on the other hand is on the left, this image is completely distorted. And the reason for that is that, yes, the camera can now do, so with event-based, we can do infinite speed 4D STEM imaging. There is no longer a bottleneck on how fast you can scan. But the scan coils are, at the moment, in a modern microscope, are not yet designed to do this. So they start to behave or misbehave a little bit at a little bit faster than 1 microsecond. So here you see, so what they need to do is they need to bring the probe back from here to the beginning of the line. And you do this really fast, but the scan coils will have some settling time to get here. So in the beginning, things are a bit distorted, and then you get to the same image again. So it's clear that future microscopes will have to improve on this aspect because there is a lot to gain. So there are 2 papers here shown, and there is much more work on this, that actually you do get significantly less beam damage for the same amount of dose compared to if you do 1 slow scan. So in this case, for instance, there are 2 fairly slow scans of 2 times 9 microsecond, and you see a material here that gets badly damaged after the second recording. And if now you spread the same dose, instead of over 2 slow recordings, over 3 faster recordings, you see that the beam damage is still taking place, but it's considerably less. And that shows that scanning multiple times, multi-frame scanning basically, can have a significant advantage in beam damage, and that is probably important for many of the materials you want to work with. And there's the same kind of conclusion here from the work from Lewis Jones, showing also that multiple scan recording of, in this case, it was EELS signals, really has a benefit for the amount of damage you do to the sample. The details on exactly how and why this happens is still very much an ongoing research topic, but okay. Okay, but that means that this fast scanning and fast frame rates is really important, not only because you want your data fast or you care for drift. Yes, this is also important, but far more important is that it reduces beam damage as well. So that's where I think the event-based cameras shine. If the frame-based cameras can get a little bit faster still, that will be also nice, and that will probably happen by working on, let's say, compression algorithms and things like that. So the only thing I still want to do is show you how we manage now to do the data treatment of this 4D STEM pipeline in real time, basically. So as the data comes in. So this is, I will show a movie where we do center of mass imaging. So you basically determine the center of mass of each diffraction pattern, but you do it inline so that basically the image builds up while you're scanning, just as you were used with conventional HDF imaging, for instance. But now in the background, there is a full set of 4D STEM data that is coming in. So here I show the results with the quantum detector's Merlin camera, which is a frame-based camera. And I have to switch off my pointer here, and then I can run it. So you will see, hopefully, how the image builds up. So it takes a while to start, and now it starts building up. A little bit as you used to see from any conventional STEM image, but behind the scene now every pixel is a diffraction pattern that you see here. And now we can start focusing, for instance, this material. So now we bring it in focus, and I think later it will go out of focus again. So this is the kind of convenience you were used to with HDF imaging, which you can now get also with the benefit of 4D STEM. But you see the image still builds up fairly slow, and that's because this is a frame-based camera which has a maximum frame rate per second, which is still somewhat limited. So that forces me to take dwell times which are still tens or 100 microseconds. I don't exactly remember what we used here. It's probably written here somewhere. I don't see it, but let's say order of magnitude 100 microsecond. Then if we go to a Timex3 camera, which in event-based, we can get this data here. So now we basically can do infinite speeds. And now you can see how quickly this 1K image builds up. And we can do live processing. Here I can probably play it again. And yeah, we see how quickly this is the virtual STEM image, and this is RICOM, so real-time integrated center of mass kind of output. But it shows that, and this shows a bit the future, where maybe in the future you will always get the result of a calculation on a 4D STEM data set while you're actually recording the data, and that's very convenient because you see your image, you can make immediate decisions on the microscope. So here's another example with an Amsterdam Scientific Cheetah Timex3 detector, where you can see exactly how fast this goes. And sorry for the sound, but you see how incredibly fast we can record this image, just as you were doing with conventional HDF. And so there is really no need to, in a way, to not record 4D STEM all the time. So there is, the technology is now at a point where in principle you can have a microscope where all your images are always, or all your STEM-based work is always recording the diffraction pattern for every probe position. The only caveat for the event-based is that this only works at low enough beam current because otherwise the camera can't handle the events. So in conclusion, I hope I showed you that choosing a 4D STEM detector can be a complex thing. There are a great number of variables, not all of them immediately obvious from let's say the product leaflets. An integrated solution where you can just buy this on a microscope and you press play, I think is currently lacking because it's still very much in development. The event-based detectors are available and they offer significant advantage for low-dose images at, I would say, nearly infinite speeds, or at least faster than your scan coils can handle at the moment. For higher dose rates, probably the frame-based have an advantage, but there is a significant speed penalty you have done. There is no fundamental reason why we should not always record all the scattering data as I showed here. Now we can, so why should we not? I mean, we are damaging our samples, we care for this information, so why only look at HDF and throw away all this beautiful information that is in the more central directions? We demonstrated live processing, so in the future this will be made entirely invisible to the operator. So if you're a researcher working on this domain, you can go into depth on reconstruction algorithms. But if you just care for your sample and you want to have low dose imaging on your whatever materials or life science samples you're looking at, this can be made entirely invisible to the operator and you can have real-time feedback. And I think this will promise better images at much lower doses, so I don't see who can be against this. And then, of course, yeah, event-based offer also other physics experiments you can do, like coincidence. I didn't talk at all about this, but this is also a very exciting development that would deserve its own, let's say, lecture.